everyone to this week's HPL seminar. Today, our speaker is Shuyue Liu. Shuyue earned her Bachelor's of Science in Sport Rehab at Beijing Sport University. She then came to the HPL for her master's degree, working with Walter Herzog. After her master's, she spent about 2 years working in physiotherapy clinics, and then came back to the HPL in 2020 for her PhD, also with Walter. Her research is focused on molecular mechanisms of skeletal muscle contraction. And outside of the lab, she is an early riser, enjoys hiking and running. So today, she'll be speaking to us about our cross bridges essential for residual force enhancement.
Hello. Thanks, Olivia, for the introduction. So today I'm going to introduce this concept, residual force enhancement, and hope after this presentation, you'll get a little bit insight how it is and what may be the possible mechanism to explain the force enhancement. So before I jump into the definition of residual force enhancement, I would like to start with some muscle structure and muscle force production. So this, excuse me, can we turn off the flashback? This figure shows the structural hierarchy of a skeletal muscle. And we have a whole muscle composed of the muscle bundles or fascicles, and muscle fascicles is made up of muscle fibers. And for one fiber, it consists of groups of myofibrils. And myofibrils are made up of sarcomeres connected in series. And the sarcomere is a basic contractile unit of a muscle. If we focus on one single sarcomere, as shown here in this schematic, the sarcomere is bordered by the Z line, which shows in white, and in the sarcomere, we have the thick or actin filament shown in green, and the thick or myosin filament shown in red. And in the myosin filament, it consists of projections of this myosin head, known as cross bridges, and be able to attach to actin. So the sarcomere can be contracted by through the interaction between this myosin head and actin, with this overlap region in the sarcomere. And this interaction allows the actins slide towards the center of the sarcomere and makes the sarcomere length become shorter and produce force along the myofibril. And this action is also regarded as the cross-bridge theory. So overall, the muscle force production is simply dictated by the number of cross bridges are able to bond to actin. And since the length of the sarcomere determines the overlap region here between the thick and thin filament, so the force production of a sarcomere is simply dictated largely by its length. So after we understand a little bit about the muscle structure and how muscle force produced, we want to know something about, some property of muscle contraction. So one of the basic property of muscle contraction is the force-length relationship. So this figure shows a modified force-length relationship adapted from the previous study done by Gordon et al. In 1966. And we can see on the y-axis, there is a normalized force, and x-axis shows the sarcomere length. In this force-length relationship, there are three parts, which is ascending limb shows in blue, the plateau region shows in red, and the descending limb shows in green. So if I have sarcomere at its maximal length, which is showing here, there's no overlap between the thick filament and thin filament. Therefore, there's no cross bridges bonding and no active force produced. So the maximal isometric force at this length should be 0, which refers to the point E in this figure. So as the sarcomere length is getting shorter, as you can see here, so the sarcomere from its maximal length is getting shorter. the overlap region between thick and thin filament is become larger. And this makes the maximum isometric force increase. So when the overlap reaches maximal level, the force, the maximal force, isometric force reaches for maximal level, which is the D point. Therefore, the plateau region shown in red in this force-tense relationship indicates the maximal isometric contraction force produced by the software. And this force-tense relationship has been established over half of the century and is still widely used in the textbook and research studies. However, the concept residual force enhancement I'm introduced today may not be fully explained by this classic study. So what is residual force enhancement? So I'm going to explain with this slide. And you can see on the left side, we have the muscle force and the muscle length. And on the y-axis is the time. And this red figure is just a simplified force-length relationship. So I will show the experimental result here and theoretical here. So if I have muscle with a certain length, like L1, based on this force-length relationship, if we activate this muscle fully and isometrically, which means there's no length change, we should have certain amount of force produced. As you can also see in this red trace, when there's no change with muscle length and with calcium present to activate the muscle, we have the steady state isometric force. And if we have another muscle set up at a shorter length, shorter than the previous one, and for this muscle, we activate this muscle at this length, and then we lengthening this muscle during activation. So if we look at this force-length relationship, it seems that the final length is the same with the previous muscle. Therefore, they should produce the same amount of force. However, with the experimental observation, we have seen some differently. So we have a muscle set up at the shorter length, and we activate it, and then we actually stretch the muscle. After the transition force is gone, the steady state force is higher than the purely isometric contraction force at the same final length. And this force increase after active stretch, or this actual force, is called residual force enhancement. So the residual force enhancement was systematically observed in skeletal muscle, but the mechanism of force enhancement remains unclear. And one of the proposed mechanism is related to the passive component in the software or in the muscle. So this mechanism is proposed based on the observation after muscle deactivate. So I took the same figure from the previous slides, and we see the force enhancement after active stretch. So when we deactivate this muscle, the force after deactivation is still higher than the purely passive stress force at the same length. So this force increase in the passive state above the passive force is passive force enhancement. Yeah. Since this force increase, like I say, is in the passive state, so we think the passive component in the muscle or software may be responsible or may explain or contribute more to this force increase. So the force enhancement and passive force enhancement has been observed in all the muscle preparations from the whole muscle level, either the whole, like a human muscle or animal, and single fibers, single myofibrils, and even single softwares. Since in the single myofibrils and single softwares, the passive contribution or the passive contributor, we think is coming from a protein called titin. Therefore, it has been proposed that this protein titin may be a major contributor to the residual force enhancement. So now let's take a look how the titin works during muscle contraction. or activation. So I have a half sarcomere here. It's a schematic from the previous slide too. And I have that line, which is the border of the sarcomere. And this is the middle of a sarcomere. I'm sorry, yes, here. And the green color shows the actin filament and myosin filament in red. So titin is a spring spans from the Z line to the middle of a sarcomere. And in this schematic, I highlight the I-band titin with this blue color, which works as an elastic spring. So during passive stretch of a sarcomere, the full titin spring can be stretched and produce certain amount of passive force. So when we stretch that, the passive force increase. And this is thought to be the traditional thinking of titin's contribution to force production, which produce the passive force. So how does titin behave during the muscle activation? So there are two proposed mechanisms related to titin stiffness increase during muscle activation, which means the calcium presence. So the first one is the calcium bind to actin. So during muscle activation, when we add calcium, the calcium may be able to bind to titin, and which makes titin become stiffer. So when we stretch the sarcomere, the stiffer titin will produce more force compared to the purely passive state, as you can see here. However, this calcium titin binding might be reversible when the muscle is deactivated, and this force increase compared to what we observed for normal residual force enhancement amount is not enough. It's like very small. Therefore, we think this mechanism may not be fully explain the residual force enhancement and passive force enhancement. And another mechanism related to titin stiffness increase is the titin-actin interaction. So during muscle activation, the proximal, the part of titin, will be able to interact with actin. Therefore, the free titin spring is become shorter. So when the sarcomere is stretched, this shorter titin element will have more strain and produce more force, which is shown here. And some studies have been shown that this titin can also interact with actin in the absence with calcium. Therefore, this proposed mechanism might be the main explanation to the residual force enhancement. And from the previous proposed mechanism, I was talking a lot about this passive component's contribution. So it seems that this element contributes is very important for residual force enhancement. So what about the active component in the sarcomere? So what's the contribution from the cross bridges? Is this mechanism, it has some association with the active component, or this mechanism is totally independent? So it seems that we don't have directly evidence to show this passive titin-based mechanism is related to the cross-bridge cycle. However, the previous study has been shown that when this cross-bridge cycle is inhibited, it's going to affect amount of residual force enhancement. So the way people used to inhibit the cross-bridge before, one way, they changed the structure from the in the sarcomere by deleting the troponin C. So I'm going to go briefly how this method works. So this is the thin filament, which is the actin filament. Troponin C is a regulatory protein attached to the actin. So when the calcium presents, the calcium is able to bind to troponin C and cause the reconfiguration of the tropomyosin. So the tropomyosin shifts from its original position to a new position. Therefore, open the myosin binding site on the actin filament. So the cross bridge can be attached and produce force. So when the troponin C was deleted, so calcium has no way to cause this myosin binding site open. So the cross bridge or the myosin head will not be able to bind to actin. Therefore, this method eliminates the cross bridge formation and with the observation from the result, is reduce the residual force enhancement. And another method people use, they involve the chemical called BDM. BDM is used as a cross-bridge inhibitor because it allows the weakly bound cross-bridge to attach, but not the strongly bound cross-bridge cycle. So this chemical disrupts the normal cross-bridge kinetic and not allowing the force production during when the mouthing and actin interacts. And similar result was found after use this BDM, we lose the residual force enhancement, or the force enhancement amount is reduced. So therefore, it seems that inhibiting the cross-bridge cycle is going to affect the residual force enhancement. And to me, it may also means that if we think the titan-actin interaction is the mechanism responsible for residual force enhancement, and when we inhibit this active component, the cross-bridge interaction, we may somehow also interrupt the titan-actin interaction. Therefore, we receive the results like reduce of the force enhancement or completely abolish the force enhancement. And also, if this speculation is true, one possible scenario would be if we repeat this kind of experiment conceptually by inhibit the cross bridges with some other ways, we highly get similar result. Either the residual force enhancement is reduced or abolished. Therefore, we search a little bit of literature and find another way to inhibit the cross-bridge cycle. So different with the previous study, people use structural or chemical intervention to inhibit the cross-bridge cycle. We use a mechanical way by stretch the muscle or the fiber with a very fast speed. And this fast stretch may cause the muscle slippage. Slippage is defined as a sudden perturbation in an active force when the muscle are stretched at a very fast speed. And it is thought to cause a disruption of the cross-bridge cycling. Therefore, the purpose of our study was to further investigate the role of cross-bridge cycling in residual force enhancement by testing the muscle with a fast stretch and disrupt the cross-bridge cycling, and to see if this is associated with a loss of residual force enhancement. So based on the literature and the previous study, we hypothesized that with our method, the residual force enhancement was vastly reduced or abolished. So to test our hypothesis, we used the fiber bundle from the psoas muscle, the rabbit psoas muscle, and the muscle strip was taken from the rabbit and tied to this wooden stick. And this muscle was stored in a skinning solution at -20 degrees for about 2 weeks before it's ready to use. And skinning is a process to permeabilize the cell membrane, but preserve the muscle structure and muscle function. Therefore, when we use the solution contains calcium or ATP, the calcium and ATP would be able to diffuse into the soft mirror and getting close to the mouth filament. And when the muscle is ready to use on the experimental day, a small fiber bundle would be isolated from the muscle strip and mounted on the testing system. So this picture shows a fiber bundle is on the system. And if we zoom this picture, and we can see actually this bundle is attached between 2 hooks. So on the left side, this hook is connecting with a lens controller. So this allows the fiber to stretch and shorten during the experiment. And on the right side, this hook connects with a force transducer to to allow the force measurement during the experiment. And if you look at this picture a little bit carefully, actually under this fiber bundle, we can see there is a bath. And this bath is used to contain different solutions. Like in our experiment, there are two solutions is mainly used. One is the activating solution, which contains the calcium, allows the fiber bundle to be activated. And another solution is deactivating solution or relaxing solution without the calcium. So when the fiber bundle incubate in this solution, it's got deactivated. So we have several baths to contain different solutions. If we have a fiber or fiber bundle attached to this system, by changing to the different baths with different solutions, the muscle can be activated and deactivated. I'm sorry, it seems this video is not working. I don't know what's going on. But basically, this video shows just like these hooks lift up, so the bundle can change to another bath with one solution and change to the other bath. Oh, it's working. It's working. Sorry. Yeah, it's like this way. Yeah. I mean, for this video, because I took a picture, it looks like a big bath, but actually, if you use that under microscope, it's a little bit tiny. Okay. And when the fiber bundle is attached to the system, before we start the real experiment testing protocol, the bundle was set up at an average software length of 2.4 micron. And this figure shows the testing protocol. So we have the average software length on the y-axis and the time on the x-axis. So for each fiber bundle, there were two residual force enhancement tests were performed. So for the first one, the fiber bundle was did an isometric reference test first, which means the fiber bundle was firstly passively stretched from an average software length 2.4 micron to 3.2 micron. And then after reached a steady state, the bundle was activated with a solution containing calcium. And we recorded this steady state force as the isometric reference force at a software length of 3.2 micron. And after that, the fiber performed a slow active stretch test. So this time, the fiber bundle was activated at the shorter length, the average software length 2.4 micron, and then actively stretched to 3.2 micron in 10 seconds. And this we refer to a slow active stretch. So we recorded the steady state force and compared to the isometric reference force to determine the residual force enhancement. So after this first size residual force enhancement experiment, the fiber will do the second one. So the difference is only the slow stretch. Now we change to the fast active stretch. So same, the fiber bundle was activated at 2.4 micron average length, and then actively stretched with a very fast speed. And this stretch was completed in 1 millisecond. And we recorded the steady state force and compare with the isometric reference force. And this slide shows the result. And we have force and average software length on the y-axis and time on the x-axis. So I will first show the result from the isometric reference force test. So when the fiber bundle was maximally activated at a software length 3.2, we have the steady state isometric contraction force. And the blue trace shows the result from the slow active stretch test. And again, the fiber bundle was activated at 2.4 micron and stretched to 3.2 micron in 10 seconds. And after the transition force is gone, when the force reaches the steady state, As expected, we see this force is higher than the purely isometric contraction force, which refer to the residual force enhancement. And this result also indicates that the residual force enhancement can be observed with different muscle preparations. So what about the results from the fast active stretch? So the red trees showing the result. So when the force, when the muscle bundle, fiber bundle was activated and actually stretched in a very fast speed within 1 millisecond, after the transition force is gone, we see the force drop to the isometric reference force level. This means we lose the residual force enhancement with this fast stretch. And if we zoom this 1 millisecond, this is how the force changed, and we have time. So from this, between these two white lines, they indicate 1 millisecond. Actually, during this 1 millisecond stretch, it seems that the force dropped during the stretch. So this may indicate we somehow interrupt the cross-bridge cycling. And our result is consistent with the hypothesis. We disrupted the cross-bridge and we lose the residual force enhancement. If we want to look at some quantitative numbers for the result, just simply we have a bar graph and shows the average stress on the y-axis and two different active stretch. So after the slow active stretch, we have a 38.1% force increase compared to the isometric reference force, but there's no difference between the fast active stretch and the reference. So we're not the only one have observed this residual force enhancement, abolishment, or reduction after fast active stretch. There is a previous study using the cat soleus whole muscle, and in their study, the stretch speed they were using is 2 millimeters per second up to 64 millimeters per second. And let's take a look at their result. And this figure shows a normal residual force enhancement. And they have the force on the y-axis and time on the x-axis. And the red trace shows the isometric reference force. And the blue trace shows the force after activate and active stretch. We still observe the residual force enhancement. And in this experiment, the stretch was done in 2 seconds. And let's see how the muscle behave with a very fast stretch. So the same, we have the force and time, and the right trace indicates the isometric force. But this time, as you can see here, the muscle was stretched super fast with 64 millimeters per second, and there's no residual force enhancement. It seems that this result assumed that this fast stretch caused the muscle slippage and somehow disturb the cross-bridge cycle and cause the abolishment of the residual force enhancement. Another example of similar result is coming from a study with the cardiac muscle. So in the literature, people shows that actually the residual force enhancement can be observed in cardiac muscle. But this study shows some different results. Let's take a look at this figure. We have stress and time. And this black trace shows the isometric contraction force in the cardiac myofibril. And this red trace shows the fibril was activated and actually stretched, and then we didn't observe the residual force enhancement. It seems that this stretch speed is also fast and be able to cause the slippage. Therefore, in their study, contradictory with the others' result, they didn't see the residual force enhancement. So overall, excuse me, it seems that the fast stretch really interrupts the cross-bridge cycling, therefore prevents the residual force enhancement. And the proper cross-bridge kinetic during the stretch phase of muscle contraction, it seems required to produce a molecular condition which allows the residual force enhancement to occur. So how can we associate our finding to the previous proposed titan-actin interaction mechanism? So why this cross-bridge cycle is needed for this interaction and to present and responsible for residual force enhancement? One of the possibility would be, so the strong cross-bridge binding is known to move the regulatory protein tropomyosin, as I mentioned before, from its original position to a new position. And this would allow the tropomyosin, this movement of tropomyosin would allow the myosin binding site open, but also the titan binding site on the actin would be open and allowing the titan to bind to actin. So when we inhibit the strong cross bridges, we will also inhibit the possibility for the titan bind to actin to make the titan-actin interaction. Therefore, we lose the residual force enhancement. So I hope you have some ideas about what residual force enhancement now. And is the isometric force after active muscle lengthening is greater than the purely isometric contraction force at the same muscle length and the same activation level. And even we think the residual force enhancement is caused by a passive element, which is titan in the sarcomere, the proper cross-bridge cycle is still essential for us to allow us to see residual force enhancement. And thank you for listening. Yeah.
Questions for Shuyue?
Can you put the speeds of the contraction that you prescribe within the context of normal human activity? Like, are these speeds something that we would expect when people are jumping and running and stuff?
Actually, like for the daily life, I mean, in the daily life for human, I don't think like people can go this fast, or like we really need to stretch our muscle with this fast. Yeah, so probably not gonna happen in the real life, but I'm not sure. But I think like in the daily life, probably we do some maximal activation or anything. Yeah, it may like we may observe like similar result if we go really fast.
Well,
yeah, but I don't have any evidence on that.
People do these kinds of experiments at the whole bone level, or the whole muscle level too, right? Like they'll do them on isokinetic machines, or whatever you call those things. You know, the Cybex stuff.
Oh, you mean like Baldex, something like that?
Yeah. So people looked at residual force enhancement on those things and looked at different speeds of.
Yeah, but I don't think they go this fast.
Yeah,
so they just do
really, really fast.
Yeah, really, really fast. Yeah,
okay.
Yeah.
Thanks.
I have a question about the timing of the reduction in force. So it looks like your forces go down kind of like an exponential, and I'm guessing that that's due to things like cross-bridge detachment rates and other stuff related to cross-bridges. And I'm just wondering, is that time constant, how quickly the exponential drops? Is that different between your stretched muscle and your non-stretched?
You mean like how the cross-bridge cycle is fast? I mean the cross-bridge cycle time with this?
Well, I'm not asking about the
because I'm not really
time, the cross-bridge time specifically. I'm just saying you're going to end up at some force, which is the residually higher force, or in the control experiment, you have the baseline force. And so there's a time course when you go down to
the relaxation.
So the difference in force is the force enhancement, but the timing of that approach, relaxation, there's a time constant to that. Is that dependent on things like, is it different from, say, just deactivating muscle or say shortening the muscle. In all cases, cross bridges are mediating that time course. So what does it depend on?
I mean, no, I don't think I have an answer for that. I didn't think about that before. Yeah, and based on this like time of relaxation compared to the deactivation. But just for my purely observation from the experiment, after I deactivate with these fiber bundles, it seems that this deactivation is faster than this relaxation. Just by purely observation. I mean, I don't have any explanation or thinking on that. But as far as I remember, yeah, I think it's the deactivation is fast. Yeah.
Faster from the isometric or from the enhanced state?
No, it's not like when compared that. Oh,
When you say faster, which is faster compared to what?
it's not compared to the relaxation of the force.
Yeah,
Like
so
Maybe you
the
can
end
show
of the
that-
stretch.
The graph again.
Yeah. You mean it?
Sure, I guess an example would be,
Uh-huh.
before you zoom in, so we see the blue curve dropping kind of exponentially, and we see the red curve dropping exponentially. I'm just wondering if there's any difference in the timing of those things.
Oh, you mean this drop? I thought you said the activation. Yeah. This one. No, I didn't like really look at that carefully. But based on this, it seems that the slow, I mean, after the slow active stretch, it seems that's slow.
So that's
Just
correct.
like
So
Yeah,
when
based
you
on
do the
this,
different
that's right. Yeah.
speeds, then with a slow speed of stretch, the relaxation will be slow. After fast, it will be fast. But the interesting thing is, when you then deactivate the muscle, it seems that when you deactivate the muscle, the force drop in the enhanced state is significantly slower than from a regular isometric state.
Well, just something I just noticed now, which I haven't noticed in previous presentations by your group, is that I always, in my head, I was thinking, oh, there's an exponential drop in the force. But actually, if you eyeball it, it's not quite a single exponential. So especially if you look at the red curve, you couldn't fit a single exponential to that drop. It's a fast drop and then a slower drop. So to me, it looks, I don't know if you guys care about dynamics, but it looks like at least a second order dynamics, which is, I think that's interesting because like if you just think about Huxley cross-bridge equations, those are first order dynamics that they talk about. So I just think it's interesting that it's at least first order.
Yeah.
More than first order.
Yeah. So probably I'll go back to my data and take a look at all of them. Yeah. Thank you.
So our former postdoc, David Core, he looked very carefully at the relaxation phase, and you're right. He fitted it with a double exponential. And he also did it for force depression. So it's the same thing. When you shorten slow, and the recovery will also be slow. When you shorten fast, the recovery will be fast. And David Core around 2007 wrote 3-4 papers exactly on that issue.
And do either of those time constants, do they depend on something like speed of the stretch or things like that? Okay.
Yeah, they do. Yeah, very strongly. The speed of stretch and also the speed of shortening when you do the reverse experiment.
So I wonder if you check whatever you said Titan was some reason for this residual force enhancement. If the Titan was intact after the fast active stretch, and the reason I'm asking that is because I'm thinking about like technically increase the strain rate, and I'm thinking about like a gum. If you move the gum very slowly, it's just gonna deform slowly with it. But if you do it very fast, it would break. And I'm wondering if any mechanism is, if you looked at the Titan and see if it was impacted.
Or you mean like if the Titan still, I mean, if we think the Titan is interact with actin, so if after this stretch we break that interaction?
Yeah.
It may happen actually, because if I took the peak force or the peak stress from this fast speed and put on like for each Titan, so it seems that the force is about like 115 piconewton per micrometer. And from the previous like experiment, I took the number from there. Yeah, it seems like when we stretch this myofibril to the same amount, to the same software length 3.2, it seems for per Titan, it can take about maybe 60 or 65 piconewton if the force is only produced Titan, assumed. But actually that's not the case, right? Because when within the overlap zone, we have cross bridge and Titan. So if we think that's outtake by Titan, it seems that my peak force is higher than that. So it's probably the possibility like we break that, but yeah, that's just what I'm thinking. It may happen. Yeah, because actually what happened inside, we don't exactly know.
You showed at the beginning these beautiful pictures where you explain with cosmic theory certain results. And then you showed the picture where you Titan and round. Can you now show me a picture where you can explain the whole thing with one picture?
Yeah. So the Titan-based mechanism to explain the residual force enhancement in one picture. Or you mean like I go back to, oh, I'm sorry. Can I go to my final slides, please?
Now, you know, if you take the left picture, there everything in there that you can explain everything that you have.
Yes. Yeah.
And
instead of like separate them to three.
Yeah.
Yeah. I just feel like yeah, that's possible. Yeah. It's probably just adding more like animation. So we're saying like just because we lose the full Titan spring, because it seems that during activation, this part of Titan we fix or like interact with actin. Therefore, we don't have enough the free spring compared to the purely passive state or the calcium binding to Titan state. Therefore,
how do you determine the point whereby
this point where to attach?
Pardon me?
So you mean this point where the Titan attached to the actin?
The transition from the white to the brown.
It's here, right?
Yeah.
Yeah. Actually, I don't have an exactly like answer for that. So we just think the proximal this part is binding. So about like what length for the Titan is binding or which region for the Titan is binding to actin, we're not sure for now. We don't really know for now. No.
Calcium is around for the white and the brown part, correct?
No, it's no calcium is here. It's because I want to show the the animation like it's bending. Therefore, I changed the color.
The white part just indicates what.
Indicates, yeah. Yeah.
So I understand that, but how do you determine where it is not found anymore? And
I
what is the reason that it's not found anymore? Because I assume that the calcium is for the whole next part. Correct?
Yeah, calcium is like binding to the whole titan. I mean, possibly, but for the titan-actin interaction, it may not be the full this titan like spring bind to the actin. So it seems like the proximal part is binding. But if you ask me like which this or like what's the length of this indicated, I don't have a certain answer. So it may be like this part band and we have more here, or we have longer band here and we have shorter.
And what does that depend on?
I don't think there is a certain conclusion on that because it seems like the experiment we're trying to prove which part is the binding. Yeah. Did I understand it correctly?
Follow-ups or?
Mine's a follow-up with this one, but. So one of the things that always kind of presents to me as a problem with this kind of idea is that in the point where you're putting stretch onto that part of the filament, right? So you're now stretching it from a previous stage to this longer stage. Aren't you also then stretching the titan at the exact same time? And so if you're stretching the titan as you're stretching the sarcomere, how would there be slack titan to go up and bind to the actin?
We think the binding is happened during activation. So if like the calcium present, not only the calcium bind to the titan, also cause the titan bind to actin during this calcium present. So when it's already binding, which means this cause the free spring getting shorter. Therefore, also with this calcium present, and after this interaction, when we stretch that, it seems like we stretch smaller amount compared to the fully.
Yeah, but why would it just bind when you don't see that without stretch? So I'm assuming that you only see the titan interaction with the lesson after you've stretched it. But when you're stretching it, you're putting stretch on the titan as well. So why in a stretch state would it bind up?
During stretch.
Or during the stretch.
During the stretch.
Right? During the stretch state where it's apparently binding and adding to the enhancing the force of contraction. Why would it bind when you're stretching?
I mean, the short answer is I
Yeah,
really
yeah.
don't know. Yeah, because I don't think
That's
someone
always
knows
one of
that.
the
Yeah.
things that I've thought about this. It's kind of appeared to me like a puzzle. Why would that happen?
I just can answer quickly. You know, you don't really see it only after the stretch. So let's say you stretch to the same length, but your stretch is short, and then you make a longer stretch. So you start at a shorter length. Then when you start from a shorter length and tighten attaches, presumably more proximal, more closer to the Z line, you expect more force during the stretch as well. And you see that. So during the stretch, you get then a higher force at the end of the stretch when you have a long stretch compared to a short one. Then they recover, then one gives you more force enhancement than the other. So you get differential forces during stretch and after stretch, depending on what length you start to stretch. So we always describe it, or residual force enhancement traditionally has been described as the steady state at the end. Because during stretch, there's a whole variety of other things happening. But if you stretch at the same speed and you think you reach a steady state and you stretch from shorter lengths, you will get more force during the stretch. So it's fairly certain that this is happening in the isometric contraction and not during the stretch or after the stretch has been completed.
And first.
You can skip it.
Oh, okay.
There's one online. Okay. In your discussion, you said that inhibiting the strong cross bridges might also interrupt the interaction between titan and actin, resulting in reduced residual force enhancement. But when you do fast stretch for your experiments, don't we still have strong cross bridges before and after the fast stretch? Do you think the inhibition needs to occur at the moment of stretching of muscle?
Okay, so the question is kind of like asking whether this disturbing the cross bridge cycle during the fast stretch. Oh, sorry.
You want to read it?
No, that's okay. Yeah, yeah. Because based on like when I zoom this fast stretch, it seems that the first drop in during the stretch. Therefore, I would assume I disrupt the cross bridge during the stretch instead of like before or after. Since before or after I observed, I mean the result, it seems like we have the nice force for the force production, but just have a force loss during the stretch. Therefore, I would say probably, yeah, we disrupt the cross bridge like during the stretch.
My question is again a follow-up. I thought this Titan isn't stiff enough because you pull it very quick, so it's a function of time or speed, stretching speed. And I thought Titan with actin and calcium bond wasn't able to occur because you stretch it very quickly. But you are saying that bond is already occurred because we have enough calcium in the solution. So the calcium bond is not a function of stretch speed. You are saying.
Say it again. I'm sorry. Calcium.
We have less force and enhancement, right? Because of the after the fast stretch. And then you said force enhancement is because of Titan, and Titan should not be stiff enough. So after the fast stretch, so we have less force enhancement. And I thought Titan wasn't stiff enough because it cannot able to bind to calcium and actin because it has a time constant. So if you stretch it super fast, and if this binding is slow, then Titan is less stiff. Is it true or? So there wasn't enough time for Titan to bond to calcium and actin because you pulled it very quick.
But I activate this fiber or like fiber bundle before.
Okay, so activation you say has nothing to do how fast you stretch the muscle?
I don't think I said like activation is doing nothing. I think I was saying like I disturb the cross bridge during the stretch. But with the residual force enhancement, with this test, it's like we activated this fiber before. We activated at a shorter length. And then during this activation, we stretch it to a longer length. So this process is happening.
I'm asking, is there more calcium bond and calcium and Titan bond? Would it be possible while
during the stretch?
Yes.
Oh, so you mean instead of like break it, is there been a possibility to bond more?
Yes, and that's what for the slow stretch we are seeing more force, and for the fast stretch we see less force because there is less binding calcium and Titan because there's a time course to that.
Yeah, I get the point. Yeah, because for the slow stretch, I kind of gave the time to allow it band, but for the fast, I didn't give it.
Yes.
It may happen. Yeah, because like from the result, it doesn't show that, like or the fast stretch, it doesn't really show what I can see for like if it's banding or not. I only see a drop, like I say, for the cross bridge getting. But yeah, this is a possibility because I don't have the number like what's the rate for the Titan and actin binding.
Can you measure the calcium amount before and after the stretch in this setup?
You mean in the solution or like attached to the fiber? Calcium should.
If the calcium amount in the solution is less after the stretch and even less after a slow stretch, then we say there is more calcium binding, right? Free calcium binding, not binding.
Yeah. I get your point. You mean like after the stretch, if the free calcium in the solution is getting like less, which probably means like this calcium is
Bind
did something with that. Okay. That makes a little bit sense to me.
That
Yeah.
may be really difficult, given the
But-
nature of the amount of buffers in the solution for calcium that exists that allow it to interact.
Yeah, well, just while we're on this slide, because I'm still trying to sort of understand it. So there's no residual force enhancement when you rapidly stretch it. In fact, the amount of force that's after the stretch and the fast is like equal to the amount of force during the isometric contraction.
After fast stretch.
After fast stretch, it's like equal. In the fast stretch condition though, are we still assuming that the titan is bound and so it's stiffer?
So you mean is titan bind to actin?
Is that happening in the fast stretch condition?
It may preserve.
The only reason I ask is that the force is the exact same amount, but you have more contribution. You theoretically have more contribution to the force from the passive tight element. So you'd have to explain the equal force by there being less cross bridges formed.
Therefore, this is compensate like to.
But that to
Got
me
the
just
eco.
it's too perfect because the forces lay right on top of each other.
I would say like there's no difference between that. That's
Okay.
an example case.
But is that how you? Because wouldn't you have to explain the relatively similar forces by a lack of cross bridges in the fast condition, but you still have this sort of increased stiffness from the passive element?
I think I get the point you mean, because like after fast stretch, it seems I lose this force enhancement. But if I use this, I mean, if this mechanism is explained that, it probably means I also lose this interaction. Therefore, the force drop to the same with isometric level. Do you think do you mean like it's contributing with cross bridge only?
I'm just wondering if I should really interpret these data as the cross bridge being essential, or if the titan interaction doesn't happen
But
when you stretch it rapidly.
yeah. But if like we don't have this cross bridge cycling, we may not even have this interaction. Like I say, like we may, we're probably gonna just like disrupting the like the troponin C deletion result. We kind of disrupting. We don't have the tropomyosin on shift, so we don't have the binding site exposed. Because the exact mechanism, like I don't think anybody knows that, but we can just have a guess if this is not exposed, or with this by the inhibition of the cross bridges, it may happen like we just don't have this interaction. But with this, if during the activation we have that, like I say for the fast stretch, either we just break the cross bridges, or like I say, like my peak force or the peak stretch is a lot higher than what Titan can take. So I may also break it, but I don't have like the directly evidence saying, okay, I break what amount for this or what amount for that to make the final or the summary to reach the same level for the force enhancement. I just have a speculation because I saw that. So I would say, okay, I disrupted during the stretch. But if you ask me like maybe how much is contribute or how much is not, I don't think, yeah, it's easy to say that. Yeah, at least for now, I don't have a certain answer for that. Yeah.
You showed a nice diagram of actin, and there's a story with myosin, which involves like calcium binds to troponin and all this stuff. So I'm just wondering, where does the titan bind? Like, do people know what the binding sites are on actin? And then is there a similar thing where calcium has to bind to something? And then
Like a
like
particular segment or something like
is
that?
there a tropotitin instead of a tropomyosin?
Tropotitin. Well, I think actually, like if for the titan actin binding, I think we still don't know the exactly component because there are some like different opinions. Some people think like if tighten binding to actin, it may happen in the PAVK region or it may happen in the N2A region. I think in our lab, like we're trying to prove which segment is exactly testing with our mom. We have a student doing that now for labeling. I think like after, I mean, if I get some results or some idea from this experiment, we probably get some insights like which segment is really binding. Yeah, that's one of the like questions we're trying to answer. Yeah, for a long time. Yeah.
Just to be crystal clear, we don't even know if titin binds to actin.
Yeah.
So I mean, this is all and hypothesis, and also I know that there is some people that have taken this as a fact that titin binds to actin, but I definitely do not accept that yet. You know, there's a lot of indirect evidence that suggests that, but there's really no direct evidence. And regarding the previous comment, about what might be happening, time constant of titin binding. Paul Edmond did a neat experiment, and then he kind of repeated it on single fibers. And that is, so Paul Edmond was saying, if titin binds to actin, and I start at the long lengths, and then I shorten, and then I stretch, but it binds now at a certain point where it initially would bind in the isometric state, then I shouldn't see force enhancement if I just go down, I slacken it, and then I come back again. And so, but the way he did the experiment, he shortened it, he waited a second, and then he stretched it. And then he actually saw exactly the same force enhancement as if you just stretched it. And we then did the experiment, and we did it that we shorten and immediately stretch back. And when you do that, then the force enhancement is all gone. And if you wait 200 milliseconds, you get a little bit, and if you wait 600 milliseconds, you get a bit more. And if you encapsulate this, if you wait about a second, then you get the full force enhancement back, which suggests to me, it's kind of what you were saying, that titin binds to actin, and yes, it binds probably when Shuyue activates it isometrically, but as you then stretch or shorten, there seems to be the possibility for titin to bind at different places. And if you bind it here in this position and you shorten and go back quickly, then you don't see a force enhancement because there's no time to readjust. But if you give it that second, then you get a completely different result. And so maybe that's what's happening here, that when you stretch really quickly, then that readjustment is not possible. Whereas if you stretch it slowly or at certain speeds, then maybe that's possible to get the force enhancement. One of the things we haven't really said yet is that when you stretch at different speed, but they're all physiological, you always get exactly the same force enhancement. So you always seem to get the same force enhancement, except when you do it super fast, then you don't get it. But if she did the stretch rather in 1 millisecond, if she did it in, I don't know, 20 milliseconds, or in 200 or in 2000, it wouldn't really matter, you get the same result. Or at least, I'm not sure in that preparation, but in other preparation. So, this is all still fairly, a hypothesis.
Early in your introduction, you brought up passive force enhancement. You're talking about how passive force is elevated. And people have been discussing, do you still have this stiff and tighten for whatever reason, whether it's calcium or binding? Do you see passive force enhancement abolishment with the very fast stretch? Fred's question about is that what's producing the residual force enhancement? Is it a blend with tight and stiffer and the cross bridges are reduced or vice versa? So I just wanted to know, do you see passive force enhancement at the end of your experiments?
For the slow stretch, for sure. After I deactivate the bundle, I see that. I couldn't remember exactly the amount, but I do see it. For the fast stretch, I would say compared to the slow, I think I still have maybe 6% force higher compared to after deactivate with the isometric. So that means like the passive force enhancement, the amount is reduced. In average, I still have this 6%, but individual is probably like a, so I mean overall I would say it's reduced or yeah.
Can you show the Cornapione slide again?
Yeah.
Because that's, to me, that's always been puzzling because.
Yeah, because they have
have
passive
no-
force
They,
enhancement.
they
Yeah.
say they have no force enhancement, and then they have a ton of passive force enhancement. I'm
There's
really
some
not sure
strange
about that
thing.
one.
Yeah.
So they clearly stretch very fast, and you see that there's a force drop there before the end of the stretch, and then the force is kind of recovering after the stretch. And then the red line is the black one, but then when you deactivate, you have these massive passive force enhancement.
Yeah,
When I saw that paper, I'm going, where in the hell is that coming from? And not only that, they actually say there's no passive force enhancement that they have, and I'm going, well, the figure that
Is
you
this
show
here?
me.
This is after deactivation, so
Yeah.
yeah.
So,
So the
I'm
force
not
is
quite
still
sure what
higher.
happens there.
I was thinking about what Osman said. I don't, maybe I missed something, but the calcium binding to titan should be independent of any cross bridge cycling, right? So that there's no force enhancement with a fast stretch. I don't know if that would that mean that it needs more time. Just the calcium binding to titan to make it stiffer. Would that need more time to bind, or does that maybe actually not happen at all?
I'm sorry, your first sentence is what, like cross bridge?
When you talked
Titan
about the ways how
interaction.
titan might be stiffer, that it could be calcium binding to titan or titan binding to actin, and with the faster stretch, we can interrupt the cross bridge cycling, but that should not affect calcium binding to titan, right? That could only affect titan binding to actin potentially.
Okay.
So when there's now you don't see any force enhancement after the fast stretch, I wonder if that means like what Osman said, that it would need more time for calcium to bind to titan, or if that just doesn't happen.
So you
Your
mean calcium
experiment
and titan
shows
doesn't
that
happen?
doesn't happen. I don't know.
Yeah, I don't know either actually.
Well, you do
Yeah.
know.
What?
Well, you have it at the beginning of your talk. What happens
Oh,
when calcium binds to titan?
yeah, it's got the titan stiffer,
It gets stiffer. How much stiffer?
about 20%,
Well,
10 to
that's very,
20%.
very generous.
Yeah, it's small
Teeny,
amount.
teeny, tiny. When
Yeah.
Venus did that troponin C deletion, or when Tim did the EDM experiments.
Yeah.
It's a tiny, tiny, tiny bit higher.
Yeah,
I would say
10%.
I would say 5 or 10% of the total force enhancement maximum. So yes, calcium does bind and titan seems to get stiffer. But I remember when we had the result with multi-ball, we were all super, super excited. Then we realized, yeah, but it explains a couple of percent of the force enhancement. So it really was not very dramatic. So the calcium binding does change the stiffness of titan, but the effect is minimal.
Any more questions?